Welcome to the video lecture series Digital Electronic Circuit S3DE for Diploma second year, BCAN 101 for BCA first year. Myself, Mrs. Mopali Roy, Assistant Professor, EC Department, Narula Institute of Technology. This is my lecture 31. Up to the previous lecture, we are discussing about the shift register, how we are getting the shift register, what is the working of shift register, how it is working. So all about the shift register or all about the introduction of the shift register. Now today we are discussing about the application of the shift register. So let's start one by one. And from the table of the counter, we know that the application of the shift register or the types of the shift register, we can say that there are two types of shift registers are there. One is ring counter and another is Johnson counter. So we are discussing about ring counter and as well as the Johnson counter. So let's start. So first, application of the shift register. What we can say that apply a serial data signal to the input of a serial in to serial out shift register. The same sequence of the data will be exist from the last flip-flop in the register chain. That means serial in and serial out. One by one input in and another input get out. So in that way, all the input get in and one by one, all the input get out from the register section. So the next part is the connection of the output of this shift register back to its input, so that the output from the last flip-flop QD, that means if we use that QA, QB, QC, QD, so the last flip-flop is the QD and the first flip-flop is QA. So the last flip-flop QD becomes the input of the first flip-flop QA. So one by one, when it is shifting, then the input of QA comes out from the output as the QD. Next, we would then have a closed loop circuit that is recirculates the same bit of data around the continuous loop for every state of its sequence, and this is the principal operation of a ring counter. So the first application of a shift register is the ring counter. So what is the application? Recirculation. That means the output of one section goes as the input of another, and if it is the output of the last flip-flop goes as the input of the first flip-flop, then this is called recirculate. That means we are circulating the input. One flip-flop's output goes another flip-flop's input in a circular way. So this is called the recirculation, and this is just like a ring. Ring means what? This is a ring. This is a ring. So if this is a ring, that means this point comes and then end in that side. So that means if this is the starting point, is goes and then again it comes to this part. So this is just works like a ring. So that is the example of a ring, or example of how ring is working. So that is the ring counter. So next, then by looping of the output back to the input feedback, we can convert a standard shift register circuit into a ring counter. So that means what we are getting, the feedback of the last flip-flop. Feedback of the last flip-flop comes to the as a input of the next one. So it's converted the standard shift register circuit for a ring counter. So let's start with the 4-bit ring counter. So this is the 4-bit ring counter, where we can say this is the logically input one. This is the 4-bit parallel output. So if we give one input, we are getting the output. We are getting this output, as well as this is the input of the next part. This is the input of the next one. In the same way, whenever we are getting the flip-flop D, that means QD again back to the next one. So First, when, see, this is preset to logic 1. Preset is logic 1. In that time, this is 1. This is clear. This is clock. Clock are the sequential one. That means all the clocks are same for all the flip-flops. So all the flip-flops clocks are same. Clears are obviously, if the preset is 1, then obviously clear is 0 condition. So clears are 0. Then what we are getting, if we give the output as input as 1, then the output from this side is 1, 0, 0. In the same way it is shifting. Okay, so this is the shifting process. That means this output goes in there. So in that way this is comes and again comes as in. So this is called ring counter. So how it is working? The synchronous ring counter example there, this one is the example of this one, is a preset so that the exactly one data bit in the register is set to the logic 1 with all the other bit reset to 0. The achieve this clear signal is firstly applied to all the flip-flops together in order to reset their output to the logic 0 level, and then a preset pulse is applied to the input of the first flip-flop, that is FF1, FFA, the first flip-flop, before the clock pulse is applied. This then placed in a single logic 1. This is placed as single logic 1 value input the circuit of this ring counter. So first, this is the input of this ring counter, that is logic 1 there. Next, so on such a successive clock pulse, the counters circulates the same data between the 4 flip-flops over and over again around ring every 4th clock cycle. That means every 4. Suppose if we are giving the clock, then when the 4th clock is there, then these input comes out from there. So for every 4th, that is the 4-bit ring counter. So for the every 4th flip-flops over the ring counter, again and again we are getting the same output. But in order to the cycle of the data correctly around the counter, we must first load the counter with the suitable data pattern as of the logic 1 or logic 0. Output each the clock cycle would make the ring counter invalid. If we are randomly changing, then it is ring counter become invalid if we are interrupting the working of this one. So this type of data movement is called rotation. We are rotationing there. We are rotationing. We are giving one input, then we are rotationing this one. So this is called rotation. And like the previous shift register, the effect of the movement of the data bit from left to right through a ring counter. What we are getting? The left to right. Left to right we are giving the data. So that is the left to right shifting. Okay. So in that way, suppose we are giving the parallel, this is in the ring, there we are getting the parallel data output, we are getting QA, QB, QC, QD, and this output goes there as the input of D flip-flop. So all are as one bit and all the data shifted there. So this is the parallel data output. So what we can see, the ring counter has the 4 distinct states. So it is also known as the modulo 4 or mod 4 counter, with each flip-flop output have a frequency value of equal to 1/4 or a quarter, that is 1/4 of a main clock frequency. That is what is modulo 4. When we are directly come to the counter part, in that time module, what is module or modulo 4 we are discussing there. Up to this is known that we are using 4-bit ring counter, so we can say as the modulo 4 also. So For this modulo or the modulus of the counter is the number of the state counter can count or sequence. That means how many number it can count. That is mentioned there. So this is the waveform. Let's check how we are getting the output. Initially, when the clock is given, in first case, initially it is 0, all are in 0 state. Then what happened? When it is given that QA, we are giving 1. When we are giving 1, then the output of QA comes 1. Then when the next clock pulse happening, then what is happening? Suppose, let's check. Suppose first initially we give it as 1. So all other are in that time remains 0, 0, 0 and 0. Then first clock we give for all these one, we are giving the same clock pulse. For all these we have given the same clock pulse. So when the first clock is given, in that time what happened? In that time these one comes there. So now the output of QA becomes 1. This 0 goes there. This 0 goes there. This 0 goes there. And this 0 comes there. This 0 comes there. So now when next clock pulse given, so when we are getting the output, then this one is 1, this one is 0, this one is 0, this one is 0. So for first clock pulse, see, this is the clock pulse 1. Let's check. QA is 1, QB is 0, QC is 0, QD is 0. Okay. So for the next clock pulse, if we give the second clock now, then what happened? This one now goes there. So this one become 1 now. This one, for this 0, this one now 0. For this 0, this one is 0. For this 0, this one is 0. And for this 0, this is again 0. So this one shifted there. This one shifted there. So first one, QA now 0. Second one 1, 0, 0. In the same pattern, when the next clock pulse is given, then what happened? This is shifting. This is shifting. So when fifth clock pulse again coming, then what happened? These QD now shifted there. So for because for fourth one, this one comes out 1 as 1. So now the input for the fifth one, the input of 0 now becomes this one. So for fifth clock pulse, this one is again 1. So in that way, repeatedly, that means for the fifth we are getting 1. For sixth we are getting this one 1. For seventh we are getting this one as 1. In the same pattern, we are getting same output. That means the output is repeating one by one. So this is the basic principle of the ring counter. Now we are come to the 4-bit Johnson ring counter. This is also a type of ring counter. Only one difference is there. What is the basic difference? Okay, let's start off with this one. Let's check what we are giving. See, there we are mentioning that this QD bar is connected with as an input. That means in case of ring counter, all the circuits are same. Q comes there, Q comes there, Q comes there. Only the one difference is QD not goes there. The output, that means the inverted output. Q is output. We give, that means the inversion output as the feedback of the basic first one. So the other circuits are same, only the difference is this one. So that is named as Johnson ring counter. So what is that? The Johnson ring counter or the twisted ring counter. It have a twist. That is, we are not using the QD. In replacing the QD as QD bar. So what we are getting? So twisted of ring counter is another shift register with feedback exactly the same as the standard ring counter above, that is, except that this time the inverted output Q of the last flip-flop is not connected back to the input D with the first flip-flop. When how shows there, that means this one goes there. So for this, the main advantage of this type of ring counter is that it only needs half number of flip-flops compared to the standard ring counter. Then its modulo number is also having. So the nth stage of the Johnson counter will circulate a single data bit, giving the sequence of 2n different state, and can therefore be considered as a mod 2n counter. That means whatever the state we are getting for the previous one in ring counter, what we are getting in the circular way, for 4 output we are getting, but in that case we are getting, if we give same input, we are getting 2n, that means 8 output we are getting from this one. So let's check. Instead of the counting therefore a fixed set of pattern like the normal ring counter, such as the 4 counter, that is start with the 0001, then for the next one 0010, then for the next one it is 0101, then it is next 1000, it is repeating. The Johnson counter counted up and then down as the initial logic one passed through the it, that is, we are replacing 1 with 0. Whenever we are giving the 1, in that case we are getting zeros. So what happened there? For a 4-bit Johnson ring counter, first back block the 4 logic, that is 0, and then 4 logic 1, therefore producing an 8-bit pattern. As the inverted output Q is connected to the input D, these 8-bit pattern continuously connected, repeated. For this example, suppose for first one, what happened? For first one, we are connecting the 1 there. So 1 0 0 0. Next one is 1 1 0 0. Then in that way, when we are getting 0 0 0 0, see 1 2 3 4 5 6 7 8. So for this we are getting 1 2 3 4 state. For Johnson counter, what we are getting 1 2 3 4 5 6 7 8 state. So that means in the same circuit, just we are using the output, that means the feedback is changing from QD to QD bar, and for this QD and QD bar only a simple change, using this only a simple change, what's happened? That is, we are getting now 2n. That means for ring counter, if we are getting 4 output, Johnson counter we are getting 8 output. So that means what we are getting, see, initially when it is 0, then 0 0 0. In case of first clock pulse 1, then what we are getting? We are getting 1. That means the first flip flop we are getting 1 output now, because the feedback is come there. So because of the, if the QD is 0, then QD bar is obviously 1. So this one as a input now. So flip flop of the first one is 1. Then shifting, this one is shifting, this one is shifting, this one is shifting. If this QD is 0, that means obviously the QD bar is 1. So this is the complemented output. So the complemented output of this QD comes there. Then this one is shifting, this one is shifting, this one is shifting. Again, this one is 0. So complemented output of this one comes there. That means 1. Then this one shift, this 0 shift. Now complemented of this 0 comes there. That means 1 came there. So 1 came there, then 1 shifted there, 1 shifted there, 1 shifted there. Now complement of this one came there. That means now it is 0. this one shifted there, this one shifted there, this one shifted there. In the same way, the complemented of these output comes there, that means this one 0, then this 0 shifting, this one shifting, this one shifting. Next, this one is now complemented output of this one comes there. So this one is 0, this 0 shift there, this 0 shift there, this one comes there. So in the same way, if the 8th clock plus pulse we are getting, then what happened? This 0 shifted there, this 0 next, this 0 next, and complement of this one comes there. That means we are repeating this 0 0 0 0 output. So what we are getting? We are getting 8 individual outputs. Okay, so let's check. This is the waveform of this one. That means if we are calculating the QD, then for first, suppose QA, so simultaneously what we are getting for first 4, that means let's check there what we are getting there. See, for if this is QA, so for 1, 2, 3 and 4 we are getting 1. For 2, 3, 4, 5 we are getting 1 there. So for flip-flop B, for flip-flop, so suppose this is our, if this is the output from QA, this is output from QB, this is QC, and this is QD, then this is from clock 1, 2, 3, 4, this is for 2, 3, 4, 5, this is for 3, 4, 5, 6. So in this way, see, this is for starting from the first one. If we are giving this one, so for first 4 we are getting this output. Next, for the next one, 1 is cancelled, 1 is shifted there, then this one is, this one comes there, this one comes there, this one comes there, this one comes there, again 0, this 0 there, this 0 there, this 0 there. For this one and this one cancel, this one comes there, this one comes there, this one comes there, this one comes there, this 0 there, this 0 there. In the same way, this one cancelled, this one cancelled, not cancelled actually, these zeros are shifting there. So this one there, this one there, this one there, this one there, and zeros come there. That means the complemented output of this one comes there. So this is the waveform from the ring counter. So for the standard 2, 3 or 4 stage Johnson ring counter can also be used to divide the frequency of the clock signal by verifying their feedback, counting and dividing by 3 or divided by 5 outputs are also available. So for 3-stage Johnson ring counter could be there used for the 3-phase or 120-degree phase shifting sequences. So this is also a wave generator by connecting the data output at AB with the NOT one. So that means this is the uses of Johnson counter. So instead of the ring counter, that means both are the shift register, also a counter, we are having the same types of connection. Only one difference is there, that is in case of ring counter we are getting the feedback input from the last output, that means QD. Suppose we are let it as QD, so from the last output, that means from QD. In case of Johnson counter we are getting this output from the QD bar, that means the complemented one. Why we are, that means the basic difference between the ring counter and Johnson ring counter is this, that instead of doing these, that means only because of these are simple change, what the advantage, we are getting 2n output. In case of ring counter, if we are getting nth output, n number of output, in case of Johnson counter we are getting 2n number of outputs. Okay, so that is the basic advantages of Johnson counter over the ring counter. Okay, so up to this is the lecture. So these are the references from where you can know about this one or the basic knowledge about this one. So these are the books or the links from where you can know about this one. So this is the end of the lecture 31. If you have any types of query, feel free to contact me. This is my mail ID and WhatsApp number. Thank you.